Okay, so now that I've described the similarities and differences between ANOVA and regression and introduced the GLM overall, I want to go ahead and run a regression, multiple regression. Fortunately for both of us, I've already clicked through all the steps and we are left with the output, so we don't have to worry about going through all those basic steps, and we can just go into the interpretation of the findings. So the first thing you want to look at when you run a regression is the overall performance of the model, which can essentially be shown by the R squared value right here. And just tying into that, Ozer's article reflects or reminds us that R squared represents the amount that one variable predicts another. And that's why we talk about it in regression, because regression is all about prediction. How well can you predict the Y value? In contrast, just the R talks about the variance that's shared between two variables, or shared between the predicted and the predictors, which we're not so interested in. We're interested in predicting. So we have an R squared value of 0.35, an adjusted R squared of 0.329. That's pretty good. Obviously, the higher the better, but if this was a real study, I'd be pretty happy to find that, especially in social sciences. So that's good. That makes us happy, and we can go on and look at more about the output here. So now that we've seen how the model overall did, we can look at the individual aspects of the equation. So as I said before, we have the coefficients for each of the predictors, and the coefficients are shown here for each of the predictors, and we also have our hypothesis testing to see if they actually are significant predictors. We also have the intercept here, which unfortunately is not significant, but we'll move on and talk about the individual predictors. So if we look at X1A, the first predictor, it has the strongest influence on the model, a weight of 0.406, so it's a very influential predictor. And we see that it is in fact a significant predictor, which is excellent. If it was not significant, we might want to actually worry about multicollinearity and this variance inflation factor, but it's significant, so no need to worry about it. We can look at our next predictor and look at the coefficient of that, which is 0.371 for the X1B variable. Again, we have a significant hypothesis test, so it is a significant predictor, so we're not really going to worry about multicollinearity. Finally, when we come to X1C, we can see there's not only a weak effect, but it's actually in the opposite direction. We come over here, we see not even close to being significant. So if this was a strong effect and then it wasn't significant, we might worry about multicollinearity and wonder if that's why it wasn't significant. But chances are, when you have this small of an effect and it's in the opposite direction, it's not going to be just the result of multicollinearity that was causing that lack of significance. But let's just say we did think that maybe multicollinearity was a problem here. We would want to look at this variance inflation factor, which is basically describes how much the standard error is increased as a result of possible multicollinearity. So correlations between the predictors that are supposed to be independent. If we got a high variance inflation factor, we might want to go and look at the correlations between the different variables and see if the predictors are correlated, or we could even possibly regress upon the individual variables and see if they predict one another, which is further evidence for multicollinearity. Now, if you did have multicollinearity, there are a few ways to deal with it, and one of the ways you could deal with it is by changing the types of sums of squares you're using. So say we had a theoretically bound reason to think that X1C was an influential predictor. Then we could possibly use type 1 sums of squares, which would and enter this variable in first into the model, which would give that priority of the variance. It would be able to take any variance associated with it and have that go into its hypothesis testing and make it more likely a significant test. But we have to have theoretical reasons to do that. So you have to be careful when you're trying to diagnose problems with multicollinearity. But that would be a possibility, but it's not something we want to actually do here. Okay, so moving forward, just looking at some of the diagnostics of this regression equation, we want to make sure our residuals, our mean residuals are 0, which in fact they are very 0, which is great. Love to see that. We also have a plot here of our residuals, and we want to make sure they're normally distributed. Obviously, it's not perfect, but it's pretty good. The mean's clumping right around 0, and that's great. So that looks pretty good. Pretty happy about that. We look at the normal PP plot, which basically shows the probability of each of these operations occurring, and you want to have them lie right along this ideal line. I mean, they stray a little bit, but for the most part, that's pretty good. Nothing to worry about there. That looks great. And so far, everything looks pretty good. The assumptions have been met pretty well. And then we get down here to the scatter plot, the plot of the residuals. And we see that there is a problem. It looks like there's heteroscedasticity. What we want to see here is we want these residuals to basically lie along a flat line, which would basically show that they're not correlated with any specific point along the variable. But it does look like there is a trend here, a pretty strong trend, and we could fit a line of best fit that would basically go like that. So that could really be a problem of heteroscedasticity, and heteroscedasticity really reflects the predictive power of our model, because for certain values, the model is going to work better than others because there's going to be more variance at certain values than others. So that can be a real problem. But the data is what the data is. Okay. And so